So last class we discussed how basically the tensor nature of chi3, right, can sort of introduce a nonlinear birefringence in a medium, right? So even though, let's say, you have an isotropic medium, due to the tensor nature of chi3, we saw that there there is some sort of birefringence introduced, right? So if you send in some elliptical polarization, then depending on its intensity, there is some rotation in the axis of the ellipse. Uh, so today, first thing, let's look at a similar effect where basically the tensor nature of chi3 is used to make, for example, an all-optical switch, right? So this particular thing uses cross-phase modulation. Okay, and you can see by again using this tensor nature, we can make something like an optical switch. So basically, let's say we have a beam of light traveling through our medium, and then using another beam of light, we can switch that first beam on and off according to our wish, basically, right? So uh, using one optical beam, switching the transmission of another optical beam on and off. So, for example, this was done. All you need is just like some length of optical fiber. Okay. So and so optical fibers are made out of glass, and glass has some chi3, right? It's an isotropic medium. So glass is an amorphous solid. It's an isotropic medium, right? And the setup is, so we have two beams, right? So let's say the direction of propagation is z, and then the transverse coordinates are x and y. Right. So we have two beams. One is called the probe, which is polarized at 45 degrees in the xy plane. Okay. So this is called probe, and this is the beam that we want to switch. Okay. So we can do that by sending another beam, which is called the pump, right? And that is polarized, let's say, along one of the two. So let's choose x. Okay, so pump is x polarized, linear polarized along x. Probe is linearly polarized but along 45 degrees, right? Or diagonally polarized. Okay. And then in the output, we have we put a polarizer whose axis is basically orthogonal to the input probe. Right? So I draw x and y. Then sort of the axis is this. So minus 45. Right? So let's say if only the probe is propagating, then basically this polarizer will block the probe because it's only letting in polarization which is orthogonal to the probe, right? So in the absence of the pump, basically nothing gets through after the polarization. Okay, so here like we can detect the output on some photodetector. right? So for example, our probe could be like a CW beam, right? So probe intensity could be like, let's say, some constant with time, and then let's say we want to put some data onto the probe, right? And let's say our pump is has some signal on it, so it's going up down up down. Let's say it has bits like 1 0 1, right? And basically we want to transfer this onto the probe. Okay. So basically we set it up such that the power in the pump is much stronger than the probe. Okay, so the pump is much stronger than the probe. And now as to these two beams are propagating through the fiber, which has some nonlinearity, right? We know that when two beams propagate, then they cause cross phase modulation, right? So one beam causes a phase. Sorry?
So information is carried in the pump or in the probe?
Pump. We want to transfer it to the probe.
Okay.
Okay. So yeah. So right. So if you want, so we can write. We know what the cross phase shifts acquired through the fiber would be, right? So the probe has two components. If we see the probe polarization, it has two components along the Cartesian axis, right? X and Y, right? So we can analyze the two polarization components sort of independently and then combine them again, right? And the two components of the polarization basically will interact with different tensor elements of the chi-3, right? So in one case, the probe polarization is parallel to the pump, both are along X, and in the other case, probe is along Y, pump is along X, right? So the tensor elements that contribute to the phase shift will be different in both cases, right? So for example, if I look at the X component, so this is the cross phase shift on the X component of probe. Right, you know, we can write the cross phase modulation as 2 gamma PL, right? P is the power in the pump, L is the length, and gamma is this effective nonlinearity, if you remember. So gamma is omega, this nonlinear refractive index N2 divided by C times the effective area, right? And this N2 we know depends on chi3, right? So if you recall, N2 is given by 3 times chi3 right, divided by some constants. So for this interaction, right, which chi3 tensor element here, if I want to write ijkl, which one will I take? So this is X component of the probe and the pump is also X polarized. So we are looking at the cross phase modulation due to the pump on which is X polarized onto the probe which is also X polarized. So what tensor element will we take there? Anybody?
With the chi3 at pump frequency.
Sorry?
With the chi3 at pump frequency. This question is.
No. So this is the cross phase shift acquired by the probe. So this is the phase shift on the probe due to the pump, right? So, we are looking at the frequency of the probe, right? So yeah, frequency will be at the probe frequency. But I'm asking what tensor element will come in. So how do we get this? How did we derive this? We started from some nonlinear polarization, right? So in this case, it will be at probe frequency. So how will we write the nonlinear polarization which gives rise to the cross phase shift? So again, we need three electric fields here, right? So we call this the cross phase shift arrives with omega probe as the output frequency, where two of the frequencies are omega pump, minus omega pump, and then the third is omega probe. Right? Omega pump minus omega pump plus omega probe will give me omega probe. It's 6 in this case, sorry, because all three are different, so it's 6. That's why we get the 2 here, right? Right? So now I want to see, so I'm looking at the X polarization of the pump. So I want to see the polarization induced in the X direction. Right? And my pump is also polarized in the X direction. So what will be the tensor elements here? Of course, the first index has to be this index, right? So that's X or 1, the 1, 2, 3 notation. And the next 3 will be?
So also will be 1.
Yeah, pump is X polarized, so it can only be 1.
Yes.
Right? So then we have pump. And then
And
probe is also at X polarized. So
X polarized.
probe is also X. This is 1, 1, 1, 1.
Yes, sir.
Right? This is 1, 1, 1, 1. Okay, I hope that's clear. So similarly, we can write the cross phase shift on the Y component. That would also be some 2 pump power times L, except let me call this gamma prime now. So gamma prime will be omega some N2 prime, because that N2 prime is now from a different tensor element. So now what will be the tensor element coming in here? So now we are looking at the probe is Y polarized and pump is still X polarized. What tensor element will come there?
So maybe 1, 1, 2, 2 or something. You are taking Y polarized.
Yeah, so two of them will be Y, right? So the first will be Y,
Two.
so or 2. And then we have 2 pumps and 1 probe. So the 2 pumps are X, so that's 1 1, and then 1 probe is 2. So 2 1 1 2, or let's, if you are working in Kleinman symmetry, then any permutation of that is fine. Okay, that's 2 1 1 2. Now for an isotropic medium, we have a relation. So let's assume isotropic and Kleinman symmetry. Then there's a relation between chi 1 1 1 1 and 2 1 1 2. Right? So if you recall, so chi 1 1 1 1 is 3 times right. So remember we could write chi ijkl as these elements times delta ij, delta kl, etc. Right? And so under Kleinman symmetry, those 3 terms are equal, and so we get chi 1 1 1 is 3 times the one with 2 of them same. Right? So basically, so this is 1/3 of this, which means n2 prime is 1/3 of n2 and gamma prime is 1/3 of gamma. Right? So basically, equivalently, I could just write this as 2 by 3 gamma PPL, where gamma is this gamma. Okay. So then we know, of course, there would be additional nonlinear phase shifts, right? For example, there would be self-phase modulation of the probe on itself, right? Which will go as gamma P probe L, but we are saying that pump power is much larger than probe power, so the cross phase shift is much larger than the self phase shift, so we neglect self phase shift. Okay. So P pump okay, so now the two components are basically acquiring different phase shifts, right? Which means at the output the polarization will not be the same as the input, right? This means that the polarization will be rotated at the output. So if you look at the phase difference between the two polarization components, that's 2 gamma PL minus 2 by 3 gamma PL. So it gives me 4 by 3 gamma PL, right? So basically I can write, so the probe polarization at the output is basically, so initially at the input it was x plus y by root 2. So at the output the x component acquires this phase shift phi x, and then the y component acquires phi y, right? So that's the, you could have normalization outside, but that's the polarization at the output. So now I do a similar trick that we did in last class. So take the common out. So the average we can take out. So e to the I phi x plus phi y by 2. And so here we will be left by I delta phi by 2, and the y component will have e to the minus delta phi by 2. Okay, and then again I can write this as some x prime plus y prime. Okay. And then you can try to relate x prime in terms of x and y prime in terms of x and y. You'll see again x prime will be x cosine theta plus y sine theta, right? Something like that. So basically what is happening, so right, so there's a rotation by delta phi by 2. Right, so my coordinate axes have rotated or equivalently. So my diagonal polarization has also, it was diagonal in the xy coordinates, now it's diagonal in the x prime y prime. So polarization is also rotated by delta phi by 2. Right. So the initial probe, so this is the axis of the polarizer. Initially the probe was, or without the pump the probe is orthogonal, so nothing gets through. Now there's a small rotation. Right. So now the power getting through the polarizer will be sine squared delta phi by 2. Right, that will be the intensity passing through the polarizer. Right, that's just Malice's law. Like you have some polarizer axis and you have input polarization, then the intensity which gets through the polarizer is the input intensity times cosine squared theta. Right. So the angle between the polarizer axis and the probe polarization is 90 minus delta phi by 2. So you get sine square. Okay. So basically, in the absence of the pump, there is no output. But whenever the pump is present, it causes some of the probe to go through, right, and be detected in the output. And so if delta phi by 2 is 90, so right, if delta phi by 2 is 90 pi by 2, then all of the probe is transmitted due to the pump, right? And delta phi we know is this value, right? So basically, if 4 by 3 gamma times pump power times length of fiber is equal to pi, then whenever the pump is present, I can switch all of the probe to pass through. Okay, so length of the fiber is under my control, whatever I want to take. Gamma is for the material given, right, glass. So I can choose the pump power which gives me. Right, so whenever the pump is present, so if you go back to this picture of switching, so if you have a probe, so let's say CW, so this is at the input, right? At the output, of course, without the pump, you get just 0. And then you have a pump which is, let's say, on for certain periods of time. Then at the output, the probe that you'll get. So whenever the pump is present, this cross phase shift will happen and then the probe will pass through. So whenever the pump is high, I'll get a probe output at the detector. Otherwise, I won't. Right. So basically, I transfer the pump pattern onto the probe. Right. Or you can switch the probe using the pump. Right. So this kind of thing can also be used, for example, for optical sampling. Right. So let's say I have some. So for in electronics, you know about digital converters, etc. Right. So there is some signal, and let's say I want to digitize it or something. Then I take samples. Sorry, is there a question?
Sir, video is goes off, sir.
Okay. Yeah, so let's say you have some signal which is varying continuously, right? So if I want to digitize it, I want to take samples at some periodic time sequence, right? And then basically sample these signal at those values, right? And then quantize it or something. So let's say I want to do that in the optical domain, right? So imagine you have a probe which has some continuous waveform like this. So let's say my probe carries, the probe intensity is something like this, right? So it could be some signal from some science experiment or something, right? Let's say something we want to measure. Then my pump, let's say, is a Modoc laser. So it is periodically giving out pulses, right? So the pump is some Modoc laser with some particular repetition rate, and let's say the pulse width is, it's like an ultra short pulse laser, so the pulse width is quite small compared to the time scale of the variation of the signal. Then basically from this you can see that whenever the pump is high, so whenever the pulse is there, then my probe will come in into the output. But whenever the pump pulse is not there, then I won't see the probe. So basically, at all the points where the pump pulses are coming, I'll sample the probe. Right, so my output will look like something like a sample signal. Right. And in the optical domain, the speeds can be much faster, right? So electronic sampling, you are restricted to 2 gigahertz rates. That's sort of the state of the art. But here you can get Modoc lasers. Nowadays, people can make lasers which have repetition rates in hundreds of gigahertz. Okay, so you can sample much finer. Okay, and also it's instantaneous sampling because the pulse width here is of the order of, like, let's say 100 femtoseconds or less, right? So basically it's instantaneous sampling. Okay, so I've posted a paper on Moodle which actually experimentally does this, all optical sampling. That clear?
Yes, sir.
Sir,
Yeah.
so here in the optical sampling,
Uh-huh.
at the output, but the intensity of probe and the output will be different, but the pattern will be same. Or that means in the optical sampling we
Yeah, you're just taking samples of the probe at periodic time intervals. That's sampling, right? So you want samples at time T1, T2, T3, T4, right? And the sampling rate is basically the interval between these two. So yeah, so whenever the pump pulse comes, you get the value of the probe intensity at that time instead.
but the intensity will be different at from the input, the output intensity and input probe
Yeah, so that
intensity.
again depends on how much rotation you're getting, right? So that depends on the pump power here, right? So we saw if you could get 90-degree rotation, then you could transfer all of the probe, right?
Yeah, and also sir, here we are taking chi as means we are taking the phase shift means taking the real part of chi and
Yeah,
neglecting the imaginary part because otherwise it become elliptical, I guess.
yeah. So again, so in optical fiber, it's made out of glass, right? So the band gap is again about 9 eV. So this resonance frequency or the wavelength, so hc by lambda naught here. So the lambda naught corresponds to about 200 nanometer. So if your wavelength is shorter than 400 nanometer, then you can get 2 photon absorption. But if you're operating at wavelengths longer than this, so typically these are done at like infrared wavelengths, a micron or longer. So basically the imaginary part of chi3 is 0 because you cannot get, just from energy considerations, you cannot get 2 photon absorption. Right? So we discussed this, that you can get 2 photon absorption only at frequencies larger than half the band gap. So, but yeah, if your wavelengths were such that there could be 2 photon absorption, then you take that into account, and that would of course distort your performance. Okay, so the next type 3 phenomenon that we study is called four-wave mixing. And there is some confusing terminology here. So four-wave mixing suggests that you have 4 different waves which are mixing with each other due to chi3 interaction, but that always happens, right? Whenever you have a chi3 interaction, there has to be 4 waves. Right, so we looked at something like this. So there are 1, 2, 3, 4, right? So basically, P3, you write something as chi3 times 3 electric fields, right? So you have 3 electric fields which are coming in here and which give rise to a polarization which generates its own electric field, right? So there are 4 of them, of course. So any chi-n interaction will involve n plus 1 waves, right? So that way, any chi3 interaction is sort of four-way mixing, but in sort of the nonlinear optics terminology, historically, four-way mixing is referred to only this kind of interaction where you have in the level diagram picture, basically 2 photons getting annihilated and 2 photons getting created. Okay. So this kind of thing is not referred to as four-way mixing. So, I mean, whenever you you see some literature, whenever you look up four-way mixing, it will be some kind of interaction like this. Right, so in general, you could have four frequencies, four different frequencies involved. And energy conservation means right, omega 1 plus omega 2 is equal to omega 3 plus omega 4, which means these frequencies lie symmetrically about some center, right? So if I divide by 2 on both sides, that means the average of omega 1 and 2 is the same as the average of omega 3 and 4. So if I denote that average quantity as something here, then omega 1 and 2 will be symmetrically about that, and omega 3 and 4 will also be symmetrically about. Right, so the arrangement of the frequencies have to be like this. And now some of these frequencies, depending on the interaction, could be same. Right, in the most general case, all four are different, but you could have two of them the same. Or we'll consider a case just now where all four are the same. Okay, and typically, so you have four. Two of them are called pumps, because typically two of these four are much stronger than the other two. Okay, so the two strong ones are referred to as pumps, and the two weak ones are referred to as signal.
The video is not visible.
And idle, yeah, one. These are weak. Yeah, so two out of these four waves have much higher intensity than the other two. Those are referred to as pumps, and then the weak ones are referred. One of them is referred to as signal, the other one is referred to as idle. Okay, or sometimes they are referred to as probe and conjugate. Okay, so for example, any two of these could be pumps, the other two could be, one could be signal, one could be idler. Right? So those would be different kinds of four-way mixing interactions, but in general, this kind of interaction is four-way mixing. Okay, but two photons are annihilated, two photons are created. Of course, they have to have frequencies like this, and two of them are strong compared to the other. So this is also, of course, coming rise from the real part of Chi3. Right, so you can see it's a parametric interaction. Energy is taken from some optical fields and transferred to some other optical fields. Right? There is no energy being lost to the medium or anything. So it's also an interaction which is arising from the real part. Okay, so we'll see some specific four-way mixing interactions now. So the first one, let's consider a case where all four frequencies are the same. Okay, so that would be degenerate four-way mixing. Okay, so all four frequencies are the same, some frequency omega. Okay, and we'll look at a specific application for this, which is called optical phase conjugation. Okay, so this is, of course, so now looks like some interaction where everything is the same, but I mean, this just looks like maybe you have only one beam, but we'll consider four different beams which have the same frequency but have different directions of propagation. Okay, so that's how we distinguish the 4 beams. So before we do that, let's just discuss what we mean by optical phase conjugation. So the motivation for this is, so let's say basically I want to image something, but there is some turbulent medium between what I want to image and myself, right? Basically, so basically, which is distorting the image. And the question is there any way to get around this aberration which is happening between the object and the observer? Is there any way to do imaging which basically gets rid of this aberration? Okay. So, I mean, the conventional way would be to.
Professor,
Yeah.
Professor, sir, in the case of two-wave, two photon absorption, also you took the same example like two photon getting absorbed and two are emitting then at the output, the same frequency, right? The diagram on the board right now.
Yeah. So that, but that, so the difference would be if this is not a real level, right? There is no energy level of the medium here. Okay.
Okay.
So what is happening is it's not actually, the medium is not absorbing 2 photons and then emitting 2 photons. This is happening instantaneously. Okay.
Okay.
But in the 2 photon absorption case, there is actually a real level here, right? So the atom actually absorbs 2 photons, goes here, right? And then it can emit. And that's the difference between, so this, for this kind of thing, the chi3 would be real, whereas this kind of thing will have an imaginary, right?
Okay. Thank you, sir.
Okay, so for example, if we have only one beam at frequency omega, and we are looking at this interaction, this is, for example, what gives cell phase modulation, right? Just one frequency omega,
Yes, sir.
right? If you have this one beam, that's basically what is cell phase modulation. But here, as I said, we'll have, although the frequencies are the same, we'll have 4 different beams. Okay, so we can actually distinguish these. They're not coming from the same beam. Okay, so yeah, so the idea is, let's say I have some turbulent or aberrating medium here, right? And I have some object here that I want to image. So typically, like in microscopy or something, what you'll do is you'll shine light from the source, right? Then you get reflected from the object, and then collect the reflected light back, right? So if this medium in between is pristine, right? It's not doing any distortions to your wavefront, then this is straightforward, right? I just collect the reflection, and whatever object is here, I see the image. But if this aberrate, in between you have some, so let's say like you're doing some microscopy, right? Your samples are inside some liquid, and that liquid is has like particles in it which are doing Brownian motion, so it distorts the wavefront. Or you have some ground glass or some, some basically turbulent medium in between that you want to image behind. So that's usually difficult, right? That's why we don't see anything behind a turbulent medium. So basically what happens, right? So let's say I'm sending a plane wave from this side. Okay, so my input so electric field profile I can write as let's consider again some monochromatic wave at a particular frequency, and this ES of R gives me the wavefront. Okay, so for a plane wavefront, this ES of R is just a constant, right? So let's say this has some polarization, it should be linear, circular, elliptical, whatever, right? And then some amplitude profile. Okay, and some phase profile. Right, so my input wave. So if the phase profile is some k dot r, then it's a plane wave, right? Or if this is a constant with e to the I k dot r, then this is a plane wave which is incident. So when it passes through the aberrating medium, the wavefront gets distorted because you can think of the aberration as different parts of the beam are seeing different refractive indices and different absorption coefficients, something like that, right? So it's distorting the wavefront here. Okay. So, and mainly we are concerned about phase, right? Usually, like we want to, I mean, if the medium in between is also opaque, which means it's absorbing or something, then of course, like then there's no way basically to see through the medium. But let's say, I mean, the medium is not absorbing; it's just sort of distorting the wavefront, so it's putting different phase shifts on different parts of the beam. Okay, so basically, what happens after this? My wavefront is very distorted. Okay, so in general, the polarization could also change. So it should become some other epsilon prime. Okay, and then what happens is it adds some random phase to my illuminating. Okay, so this phi s of r is due to the medium, which has some very complicated profile. Right, so this is now multiplied with my input. Okay, now I go to my object and then let's say I reflect off. So in a conventional case, let's say this is a conventional mirror, then the wave which is coming back will just be reflected, right? So all that will happen is this k will become minus k, right? So this wave which is coming back has same polarization, same phase profile. This now becomes e to the minus ik dot r, right? So there's a reflection. And then when it passes through the aberrating medium again, basically it will add this distorting phase once more, right? So the thing coming back here to me, which I collect, right? And it will, if it distorts the polarization, it will distort the polarization even further, right? So now it will become some epsilon double prime. And here I'll get e to the I2 phi s r. So all the, you can think of the distortions are doubled basically, right? So they become worse. switching between top and bottom. Okay, so basically the wave that I receive has sort of double the distortions of a single pass through the turbulent medium. Okay, so basically it's hopeless, right? So now, let's say instead of reflecting here from like a conventional mirror, if you could have something which is known as a phase conjugate mirror. Okay, so what is a phase conjugate mirror? It's a mirror which conjugates my input field. Okay, so here my input field was this, right? So all the phase variations are negated. This becomes okay. So when I take this minus sign, you can see basically what's happening is these distortions are now opposite. Okay. So sort of if I show the distortions happening in the direction of propagation, now for the reflected beam it's sort of opposite to the direction of propagation. Right? So actually this, yeah. Okay. And now you see that when now if I pass through the turbulent medium again, now it will add this phase distortion again, but now I have a minus sign. Right? So basically I have a negative of the distortion already on my wave, and then I add the distortion, so basically this goes away. Okay, and basically I have eliminated my phase distortion and I get my plane wave back. Okay, so basically if I could take the conjugate of my phase profile here, so basically after one pass through the medium, if I could take a phase conjugate and then pass again, then that basically nullifies the effect of the turbulent medium. Okay, and I get back my sort of illuminating beam. Okay, and then basically I can image whatever is here distortion free, because this effect of this is completely gone away. But, so for that I need something which takes the conjugate, right? So basically one way to do that is through this four-way mixing, right? We can do this optical phase conjugation, which can be applied to imaging through distorting media, right? So just to give you sort of a little more insight into what this phase conjugating mirror or how strange this phase conjugate spin mirror is. So for conventional mirror, if I have some wave incident like this, then I know that the reflected wave will go like that, right? Which is basically coming from the fact that the transverse wave vector, right? So if I call this as z and this as x, and this is some e to the I k dot r, which has e to the I k z z plus kx x, right? So for the reflected part, the kx x is conserved, right? The transverse wave vector is conserved, and this longitudinal is reflected back. So that's why the direction is reflected back, but the transverse wave vector is conserved, right? So that's why the reflected ray looks like that. But now let's say you have a phase conjugate mirror. If I have an incident wave like this, right? So I have some input phase which looks like that, and then direction of propagation again is z, right? So when it reflects, it will take the phase conjugate here, right? So kx will actually become minus kx, and of course kz becomes minus kz. So you can see that that would mean it actually comes retraces back. Right? So if you have a perfect phase conjugate mirror, then if you shine any ray on it, the reflected ray will actually retrace the path back. So now you can imagine what happens, let's say if you stand in front of a phase conjugate mirror. So if we stand in front of, so let's say this is me, right? I'm looking at a mirror. So what do we see? We see a reflection of ourselves, right? So it's basically the virtual image which is being formed, right, on the other side. So basically you have rays reflected like that, and sort of image being formed like that. So now let's say there was something like a phase conjugate mirror, and I'm looking into the phase conjugate mirror. What would you see?
So
So
reverse version, head down and legs up, something.
head down and leg up.
Or nothing, I don't know.
Think about what the phase conjugate mirror does, right? So
Reverse, na, it do
so
the
okay,
same.
what do we see? We see finally the image that is being formed in our head is the rays which are falling on our retina, right? So so imagine whatever is causing an image is finally rays falling onto our retina, but what are the rays which will come and fall into our retina?
So the reverse image will be formed inside the retina. Whatever the image is there, the reverse is formed inside the retina actually.
Yeah, so it will be something like we'll see a retina,
Okay,
right?
sir.
So the only rays which can come and converge on my retina are the rays which go out, because the phase conjugate mirror just reflects along the incident path, right? So whatever rays are converging into my retina have to originate from my retina, right?
Okay.
So basically I'll see how my retina looks,
Okay.
right? That's I mean, of course, there is no perfect phase conjugate mirror available for us to do this, but for certain directions, for certain frequencies, you can make a phase conjugate mirror using photon mixing, which we'll see. Like to see something like this, you need a perfect phase conjugate mirror which works for all angles, for all frequencies right across the visible spectrum to see the whole image.
So, what will the material composition of this phase conjugation mirror?
Sorry?
Material composition, like material property of this PCM.
Yeah, so we'll see how so it's not just a material on its own, right? Basically, to do that phase conjugation, we need something which does the phase conjugation, right? So we use nonlinear optics to do that, right? So it's not just a medium on its own. We need, so in some sense, it's like an active medium. We need to pump. It's a nonlinear medium, plus we need to pump it with some lasers to make it act as a phase conjugate. So we'll discuss that next. Okay, so now, yeah, so let's imagine you have some chi-free medium here. Okay, and I have some two strong pumps. So two strong waves counter propagating to each other. So for example, it could just be one wave and then I could have some mirror here which retro reflected back. Okay, so I have some two strong waves, both at frequency omega. I mean, so we'll consider degenerate photon mixing. So we consider 4 beams, all of them have frequency omega. Okay, so this is, let's say, wave 1. So 1 and 2 are so-called pump beams, which are strong. Okay, and basically this thing will act as a phase conjugate. Okay, so this chi-free medium with these two strong pumps will act as a phase conjugate mirror for any weak beam coming in here. Okay, so there's some third wave coming in here, A3, which I can call, let's say, the signal. Okay, it also has the same frequency. And there'll be, due to the chi-free interaction here, there'll be a reflected wave, you'll see, and that will be the idler or the conjugate. Okay, and this reflected wave we'll see has the conjugate profile of my input signal. Okay, so the setup is that so A1 and A2 are pumps, which means so A1, A2 much larger than A3, A4. Right. And now so there are sort of two directions of propagation. So let's call this, the horizontal one, as Z, and then this diagonal one as some Z prime. Okay, so the input of the material here is Z equal to 0 in this direction up to, let's say, Z equal to L. And the pumps are in some Z prime direction, which is at some angle Z. Okay, so we can write the electric field corresponding to each of the waves. So right? Where so I here is 1, 2, 3, or 4, right? And basically, our setup here is that K1, direction of K1 is opposite to K2, and similarly K3 is opposite to K4. Right, so we have 4 beams which we are distinguishing from their K vectors or directional propagation. They are the same frequency. Okay. So now, if you look at the nonlinear polarization, or the third order polarization, of course we want to look at the frequency omega, because all the waves are at frequency omega. So that would be something like this phi 3 then mod e square e. Right, because all the waves are at omega, and I want something which the polarization at omega, so I need omega, omega, and minus omega. So I need e conjugate e. Right, which also from the level diagram I get omega, omega, and then this will be minus omega. Coming down will be minus omega, which gives me the remaining at omega. Right. So now, if I look at the nonlinear polarization, that will have components in different directions. Okay, so we can write the polarization as again having some phase, right? And that like the resultant wave vector of the polarization would be basically which fields we choose to put here. Okay. So, for example, okay, so we know the nonlinear polarization acts back on the fields, right? So, for example, if you want to see something which acts back on my signal, so wave 3, so wave 3 has polarization e to the I k3 k3z, right? So if I have a component of the nonlinear polarization which also has phase e to the I k3z, that will directly affect my signal, right? So in the canonical propagation equation that we write dA by dz, and then on the right hand side I have nonlinear polarization, right? So that nonlinear polarization on the right hand side, if it has the same wave vector or the phase relationship, it will affect that way, right? So, for example, so I could look for components which go as k1z, k2z, k3z, k4. Right. So, for example, if I want to write p1, right. So p1 is the coefficient of the term which is going as e to the I k1z, right? And I get that from mod e square e. So how can I get k1? Right. So here, basically for e, I'll put some ai e to the I ki z here, right? For each of the e's or its conjugate. So how can I get K1Z from these. So I need to choose 3 of them, right? I mean, all 3 could come from the same or different, right? It's something like when we want to write how can we get this output frequency here as a combination of different frequencies. Here we are just looking at the k vector because the frequency is region, right?
So, sir, one frequency would be negative of the other, so the other two cancel and only one be left off. Something.
Yeah. So okay. For example, I could get K1 as K1 plus K1 minus K1. That's one way to get K1,
Yes, sir. Yes, sir.
right? So this K1 2 times will give me A1 square, and minus K1 will be A1 conjugate, right? So this is basically mod A1 square A1,
Yes, sir. Yes, sir.
right? So that's one term that I can write here. But there can be other terms also, right?
Yes, sir.
So other ways I could, so instead of 1 I could just replace 2. So I could have K1 plus K2 minus K2, right? So that would give me A1, and then here A2 conjugate. So that's mod A2 square A1. And we need to keep track of the degeneracies for each of them, right? So I've already put 3 here. So of course, so for K1 it was 3 because there are 3 combinations. But for this K1, K2 minus K2 there are 6, right? So there is a 2 here. And you can recognize these are basically what? What is this term?
So E conjugate into E, matlab one frequency is negative of the other, so you will get the mod.
No, but where have we seen this kind of thing before? In what phenomenon we were discussing? We wrote the polarization like this,
Phase
right? So
modulation.
yeah, this is self-phase modulation, right? So this is something like the coefficient of A1 is something like which will give me refractive index, and that has mod A square, mod A1 square. Right? P1 is basically what will affect A1. Right? So this is self-phase modulation. What is this?
Maybe crossfade.
This is cross-phase modulation, right? So this is the phase shift that 2 puts on 1, right? And it has a factor of 2 here, as we've seen before. And there could be additional terms also, right? So this could be 3, for example, but then that would give me A3 square. And basically, we assume that 1 and 2 are much stronger than 3 and 4. Okay, so basically we say that keep only linear terms. In A3 and A4. Okay, so if I get A3 square or something, A4 square, I neglect those terms. Okay, because A1, A2 are much stronger, so mod A1 square, mod A2 square will be much larger. Okay, is that clear? Similarly, I can write P2. What would be P2? So that goes as either the I K2Z or K2Z prime. Let's see, this is Z prime. Be vectors here, I guess. Yeah, ideally maybe I should write. So what will be P2? What terms will I get for P2?
Sorry, mod
You just replace 1 by 2, right? It's the same thing. So mod A2 square A2. That's the surface modulation for beam 2. And then 2 times mod A1 square A2. That's the cross phase modulation from 1 on 2. Right? There'll be other terms with 3 and 4, but you can see
Yes, sir.
any term. Sorry?
So we don't have to find the relation between with A2 and A3, A4 or something. We have to find in the term of A1 only. Like,
No. So what I'm doing here is this. We'll keep only the linear terms in A3, A4. Okay. So any other term that you want to write which has 3 or 4, you will see we'll have at least two A3 or A4. Right. So for example, how can I get K1? So I can get K1 as, for example, I could get it as K3 plus K4 plus K1, right? Because K3 and K3 is equal to minus K4. So I could also get K1 like this. So, but what are these terms? So I'll get an A3 if I want e to the I K3 dot R. Then for K4 I want A4 and A1, right? But A3, A4,
conjugate.
both A3 and A4 are small. Okay, so it's like some small quantity, and I want to keep only linear terms. So this is like square in the small quantity. Okay, so I neglect. I don't.
Okay,
I
sir.
neglect that compared to. So I'm saying mod A1 square and A2 square is much larger than A3, A4. Similarly, I could have K3 minus K3 plus K1. Right, this would give me mod A3 square A1. Now again, mod A3 square is square in the small quantity, so it's much smaller. Okay. So any other term which has 3 or 4 will be square in the small quantity, which we neglect. Okay. But we'll see for P3, P4 we'll have terms which have. Right. So now let's write P3 and P4. So if I want to write P3, what are the terms I can write?
Sir, K3 plus K1, K2. K1, K2 cancel each other, so we'll get the K3.
Okay, so we're saying I can write K3 as K3 plus K1 plus
K1
K2
plus K2. Yes,
plus
sir.
K1 and K2 are opposite. Yeah,
Yes.
so that will give me A3, A1, A2.
A1, A2. And sir, one more thing is K1 is minus of K2. The amplitude will be same, sir. Like A1 equals to A2. Like they will become the conjugate or something. No,
Yeah,
no.
I mean, in general, if you're sending two beams, they could be different.
Okay.
But eventually, we'll assume A1 equal to A2 just to make the math a little
Okay.
bit easier. And that's how typically, like in the experiment, also you just have to shine one beam and then retro reflect it back, so the intensity is the same.
Okay, sir.
Okay, so
this wrong?
I mean, actually, this is the same thing, right? So I could write it as okay. So I could get K3 as K3 plus K1 minus K1. So this is again mod A1 square A3, right? K1 and minus K1 A1 conjugate, and then yeah, K3 from A3. So that's the cross phase modulation from 1 on 3, right? Again, I put 2 here because there are 6 permutations for this. Similarly, I could have the cross phase modulation from 2 1 to 3. So this could be K2 minus K2. Right? What other terms? I could also write like a self phase modulation term, mod A3 square A3, but again, that's square in A3, or so we neglect, right? Could there be other terms? Would there be any other terms here?
A1, A2, and A3.
A1.
In the previous one, like
Yeah, I guess you could also have A1, A2, A3. Any other term?
Conjugate the A1 conjugate A2 conjugate A3.
Sure. You also have do you have any other term? What about any term with 4? Could we have any term with 4? We only have, we consider terms with 1, 2, and 3. So could something with A4 come here, contribute here? I mean, you know that K3 is equal to minus K4.
twice of something, twice of A3 minus K4, something.
Yeah, but twice of K3 again will give you A3 square. So that's small.
Okay.
But I could have, like, for example, K1 plus K2 minus K4 K1 plus K2 is 0. So this gives me minus K4, which is K3. Right? So this would be A1, A2, and A4 conjugate. So minus K4, right? So I could have A1, A2, A4 conjugate. Right? Is that clear?
In this case, the A3 should be equals to A4, then only this term will be considered, right? A1, A2, A4 conjugate, the bottom one, sir. So when you are calculating K3,
Looking at terms which go as, so we wrote the polarization as the total polarization as I'm writing K1 plus P2 and I'm just doing this. So I want to look for terms. So P3 are the terms which go as e to the I K3 dot R. So which terms will go as K3? K3 dot R. This term will also go as K3 dot R, right? I'm not looking for something times K3. I mean, I would look for that if I wanted to define something like a refractive index or something, right? But here I'm looking at the entire interaction. In the 1 and 2 case, or I mean, because we're neglecting the small terms, we only had terms like this. Okay.
Also, their conjugate. A1 conjugate, A2 conjugate, A4 conjugate.
I mean, from here you can guess something like that the 3 will be related to 4 conjugate, right? 3 and 4 will be conjugates. Let's see from that's where from where it comes, basically, right? Okay, is that clear? Can we proceed? Yes? Yeah.
yes, sir.
To erase something. So similarly, we can write P4 right? So P4 basically I replace 3 by 4 and 4 by 3. Right? It will be the same. right? So this term is actually the four-way mixing term. Because all the other terms have A3, so they're like phase shift, right? So remember how we got the nonlinear refractive index and the self phase and cross phase shift? We got P is equal to something times the field, right? So these terms are like that, have A3 in the end, but this term doesn't have A3, it has A4 conjugate. So that's the four-way mixing term. Right? So it's like the two pumps are mixing with the conjugate to give me the signal. Similarly for here we have the cross phase modulation terms. So this plus E1, E2, E4. Plus a four-way mixing term which goes as A1, A2, A3 conjugate. Right? Okay, so now we have the nonlinear polarization, right? So then we can see how the fields are affected using the canonical propagation equation, right? So for example, dA1.
Excuse me, sir. I have
Yeah.
a doubt.
Yeah.
So we are considering the terms twice of A1, A2, A4 and A1 conjugate, A2 conjugate and A4. So why we are not considering the four-way mixing conjugate part?
Four-way mixing conjugate part.
A1 conjugate, A2 conjugate and A3 conjugate.
So in P3, you're saying there's an additional term or?
Yeah, means there is another term that is A1 conjugate, A2 conjugate and A4 conjugate.
A1. Yeah, sure. I mean, um, okay. I think we made a mistake, right? So remember, we were also looking at the terms which go as the frequency has to be omega.
Yes, sir. From that A1 conjugate, A2 conjugate, A4 conjugate, we'll get minus of.
So, for example, this term should not be there, right? A1, A2, A3 actually gives me frequency 3 omega, right? Because each of them will
Right.
give me e to the I omega t, I omega t, I omega t. So 3. So this term should not be there. Right. That's why we need we can only have one conjugate term. So this one, for example, omega minus omega omega, omega minus omega omega. So that's giving me omega. This is giving me omega. This is again omega minus omega omega. Now this one, A1 conjugate, A2 conjugate, A3.
Minus omega.
This is giving me minus omega. So this should also not be there. This one is giving me omega plus omega minus omega. So this is omega, right? So this one should be. But now the other term that you're talking about, A1 conjugate, A2 conjugate, A4 conjugate is giving
Minus
me
3 omega. Minus 3 omega. Yes, sir.
right? So that's also not at the right frequency. Right? So that kind of term, if you're doing some third harmonic generation or something, then you need to consider that. Right? But we are only considering the terms at frequency omega, so that's the only term. Yeah, similarly here actually these terms are not there. That's why I got confused a little bit. Yeah. Yeah, so that's why this kind of interaction helps. You know, to it helps me also correct my mistakes. Okay, so yeah, so P3 will have only 3 terms: the cross-phase modulation from the pumps, and then the four-way mixing term. Similarly, P4 will also only have 3 terms: the cross-phase modulation from the pumps, and the four-way mixing. Yeah, actually, similarly here, I mean, you could have written more terms, other terms also, right? Like mod A1 square A2 conjugate, but that's at frequency minus omega. That's why we didn't consider that. Okay, so now, yeah, so maybe I should explicitly write this as at frequency omega. Okay, so then these are the only terms. I hope that's clear now. Yes? No?
Sir, yes, sir, clear.
Yeah. So now, once we have the nonlinear polarizations, then we can go on to the propagation equations, right? So, for example, the propagation equation for pump 1. So remember that was going like this in the z, some direction which we call z prime. So on the right hand side, I have some constant times the nonlinear polarization. Yeah, so maybe to make it clear, so let's write the. So if you recall, the canonical propagation equation was some constants here. So that's the canonical propagation equation, right? So basically, we need to just write this for 1, 2, 3, and 4. So you can see that A1 will be driven by P1, right? Because P1 has e to the ik1 z there, which will get cancelled with the e to the minus ik1 z. Okay. So that will be the equation for 1. Okay. Because I mean, in general, I could put the whole nonlinear polarization here, But these other terms, P2, P3, P4 will go as e to the I k2. So you'll get some term as e to the I k2 minus k1z, right? Which will average to 0 when we average over z. So it's something like phase matching, right? Only the k1 term here will get exactly cancelled out. So with that, that's why we take only the p1 term for k1. And yeah, 2 is exactly the same, except the direction is opposite, right? So remember 2 is counter propagating to 1. So for 2, I just have a minus sign because like there's a minus sign here, right? So it's propagating in the opposite direction. So I just take the minus sign here. Okay, so this is for 2. Basically, only the P2 term will come here. Right, so you can see the equations for A1 and A2 look like something times, right? So dA1 by dz is something times A1. So this looks like a phase. Right, similarly for A2. So A1 and A2 just acquire phase shifts, which is a combination of the self phase and cross phase. So the solution to A1 and A2 is straightforward. Right? So A1z I can just write load some again. So the solution for A1 of z prime is just sorry guys, just 1 minute. So solution for A1 just some phase, right? I can write like this because this is just a constant. So this whole thing, if I write as kappa, so the magnitude of A1 and A2 remain the same. And they just acquire phase shifts. Minus here. Okay, so now we assume for simplicity that that the two pumps have the same intensity, or it's just one beam which is being reflected back, so it's the same intensity. Okay, so then this factor is the same, you can see, right? Mod A1 and mod A2 are the same, then this whole factor is the same for 1 and 2. So one goes as e to the I kappa z prime, one goes as e to the minus I kappa z prime, right? Both of them just acquire phase shifts. Okay, so it's basically this kappa is just a nonlinear phase shift. Okay, so omega by c n2 times I. So here I have 3 times I. So I into I, simply I into I. Okay. So what does this mean? If I write, so this means that A1, A2 basically doesn't change with propagation, right? So A1, A2 at any z prime is the same as A1, A2 at 0 because they're counter propagating and acquire phase shifts in opposite signs. So A1, A2 at any z prime is the same as A1, A2 at 0. Basically that helps us simplify the equation for 3 and 4, right? Because we get A1, A2 here. But we can just say A1, A2 is independent of that, it's just a constant, like the input intensity. Right, so if I write now the equation for 3 and 4, which is like the signal and conjugate. So dA3 by dz right, I get that. And 4 is same, so it's 4 is traveling in the opposite direction, so it's minus here. Okay, so I get these two coupled equations for 3 and 4. We know that mod A1 square, mod A1 square, mod A2 square, A1, A2 are constant quantities, right? They don't change with propagation. So we'll see A3 and A4 are the ones which change with propagation, and they're coupled to each other using that with that conjugate. So dA3 by dz goes as A4 conjugate, dA4 by dz goes as A3 conjugate. You can already see they result in something like phase conjugation, right? because they're taking the conjugate of the other. Right, so when we have these solutions for A1 and A2, then basically mod A1 square is equal to mod A2 square is equal to A1 A2, right? They're all constants. The input intensity, right? So basically, I can rewrite the equations like this. So kappa 4 is equal to kappa 3 actually. Right, where kappa 3 should be an A3 here, right? It should be an A3 and A4 here. So the coefficient of A3 is kappa 3 and the coefficient of A4 conjugate is kappa. This is the same kappa that we got for A1 and A2. Okay. And yeah, kappa 3 is basically, if A1 is equal to A2, you can see it's just sort of twice of kappa, right? Okay. So basically, we are getting coupled equations between 3 and 4, right? So the coupling constant is sort of this kappa, and you can see A3 is coupled to A4 conjugate, A4 is coupled to A3 conjugate.
Professor, this A3 and A4 values are very less. That means coupling will be less.
No, so the coupling constant kappa, you can see depends on the intensity of the pumps I1 and 2.
Okay, sir. Okay.
right? So the coupling constant depends on the intensity of the pump, which is strong. Right? Okay, so we can simplify these equations a bit further. So we take, we do a change of variables basically. So basically, I mean, if it would have been easy to solve if we didn't have these terms, right? If we just had dA3 by dz equal to something times A4, dA4 by dz equal to something times A3, then we sort of know how to solve them, right? But we have these sort of self-phase terms which are coming in here. So we can get rid of them by doing a change of variables. So if we do A3 prime is equal to A3 minus I kappa 3 Z. And similarly, A4 prime right. So and basically rewrite this equation in terms of A3 prime and A4 prime, which are just the original amplitudes multiplied by some phases, right? So you can see when I do dA3 prime by dz, I'll get something like, so when I do the differential of this, I'll get IK3 times this thing, so which will get cancelled. Okay, so just do a change of variables here and write the equation in terms of A3 prime and A4 prime. You see that these terms go away, the self terms go away, and only the cross terms remain. Okay, so we end up with these two. So now we can directly see 3 is coupled to 4, 4 is coupled to 3. Okay, and now we know how to solve these equations. It's very easy, right? So you just differentiate this again. You get dA4 by dz, which you can use this. Right. So here now you can finally directly see that A3 is driven by the conjugate of A4, A4 is driven by the conjugate of A3. Right. So for example, if I differentiate the equation for 4, then you get this, and now dA3 by dz I can use from here. So in general, kappa could be a complex number, right? Because let's say A1, if A1, A2 had some phases initially, then it could be a complex number, but without loss of generality, we could also just call it a real number, right? If we don't take those. If there was a phase difference between the retroreflected pumps, then we'll just have some phase here. So K could be a complex number. So that's why I'm taking K conjugate. But finally, you can see only mod of K square terms. So anyway, it's irrelevant. Right. So basically, the equation becomes right. So d square a4 by dz square is minus mod kappa square a4. So the solutions are sines and cosines, right? So I can write a4 prime, the solution as c1 cosine mod of kappa plus c2 sine right, and then a3 I can get from dA4 by dz. Right, so I have solutions for A4 and A3, and I need to determine constants C1, C2, which we'll do from boundary conditions, right? So we are past 5 o'clock, so maybe we'll continue from here next time. Okay, so basically what remains to be done is find these constants, then find the solution for A3 and A4, right? So A3 is the input signal and A4 is the reflected conjugate. Right, so setup is like this: A1, A2, A3, and A4. So we just need boundary conditions at z equal to 0 and z equal to L to find the C1 and C2. Okay, so we'll continue next time. Okay.
Okay, thank you, sir.
I hope it's clear so far. I mean, in between we sort of lost track a little bit, but I hope
Yes, sir.
any
So
confusion was.
this
Sorry?
thing also we have to study from Boyd book only.
Yeah, so far mostly what is covered is from Boyd's book.